Give me a second here. I have to click like 5 different things here. Move one thing out of the way, move another thing out of the way. Okay, so I can actually see what's going on. Take a drink before I lose my voice here at the start. Okay, I'm starting the textbook material today, chapter 1. And this kind of applies to all computer science. It probably applies to all disciplines. Is that in the opening we kind of take a broad view from say 30,000 feet, and then over time we look in further more and more detail, and that's true for computer science. And especially at the beginning, we look at the classifications, the categories, things like that. You look at biology, same thing. Kingdoms, phylums, genus, species. So we classify, we categorize. So a lot of this chapter, this first chapter, is just that. And we come back to each one of these topics over and over in more and more detail. So, okay. One of the things, and what I've really just described here, is abstraction. But abstraction really is part of computer science, because there are so many discrete, when I say discrete, small details. So it makes sense to actually look at the big picture in many different ways, many different avenues. So abstraction. What is abstraction? It's removing those details so we can look at the big picture. We do this every day. You get in a car and drive. I have a steering wheel. And I'm not actually thinking about the angles of the tires, things like that, about how it's making me turn. I just use it. I use the general properties that are necessary for me to do what I need to do, the brake, the accelerator. I could care less about the timing of the engine. So that's abstraction. It's even more important in computer science because we're going to look at down the road in a chapter, symbolic representation. Of course, if I want to, simulate a traffic light, something like that, a traffic simulation, I can't put cars, traffic lights like that, things like that into the computer. I need to represent them. Do I need to represent all aspects? No, I just need to represent the general qualities that are, applied to that simulation. So abstraction and symbolic representation kind of go hand in hand when we're looking at our early studies in computer science. So what is a computer? What does it do? Okay. Here's the definition, and probably the first word here, programmable, is probably the most important because it really distinguishes the computer from other machines. In my first class today, as my wife was going by with a snowblower, that snowblower does one thing. A sewing machine does one thing. A computer, because of the software, can be run, provide different functionality on different data sets. And that's very important. It was really a big step forward. So what is it? It's a programmable electronic device, accepts data, performs operations. Okay, we kind of know that. The basic operations: input, processing, output, and storage. Now, moving forward, you're responsible for what the textbook states. In essence, what we're stating is everything in the textbook is 100% correct. It's not. I'll alert you to where the textbook is wrong, but you're actually responsible for the textbook material. And actually in the quizzes, I've tried to remove, because the quizzes come from the publisher, from the authors, I've tried to remove the questions that were misleading or incorrect. It's sometimes hard for me to do that just because I've studied. I kind of see where the authors were going with that, but it may not be the best representation or the best way to ask it. I state that now because in most textbooks, you will not see storage as a part of the basic operations. In a lot of textbooks, you'll just see input, processing, and output. That's it. If I look at, my browser here, up in that location bar, I could type in, 2 plus 3, and it'll return to me, the answer 5. That value was never stored, okay? So storage, output is stored quite often. Sometimes it's never stored. Sometimes it goes straight to communications. So again, this textbook, though, will say textbook is correct. So the basic operations: input, processing, output, storage, okay? And then also communications. And this definition scales across different levels. We'll look at the CPU, the central processing unit, and it'll get input, through the registers. It'll perform processing and perform output. And by the way, the CPU does not store. Storage is like a hard drive or SSD. The end result may remain in a register, which is volatile, or it may just go back to memory. So again, storage is not a component of every operation. This input processing output model also applies to, say, a computer. I can type along here, input, the computer does some processing, and it provides me output on the monitor. It also scales up to a full-blown information system. As you register for your classes, you put your schedule in. There's processing, financial aid, things like this. It outputs a schedule for you. It outputs a schedule for me. Okay, so this input processing output cycle actually applies to every level throughout computing. So the basic operations, again, input, processing, output, and we'll say storage, and we'll also acknowledge communications. Data versus information. Okay. Data is the raw, unorganized facts. Can be text, graphics, audio, video. Okay. Information, it is data that has been processed into meaningful form. It's been provided context. And of course, information processing is that conversion from data into information. So let me give you an example. This is not in the textbook. Look at this number, raw data, 012569856. I just typed this out of my, just kind of created it. And I asked the question, does this mean anything to anyone? And some people can kind of guess sometimes, okay? But again, that's guesswork. And in computer science, we don't guess. True, false, no ambiguity, okay? There's no multiple paths. We always have a clear decision path. So if I take that number and put it into a table and give the table a heading, SSN, immediately everybody knows what's going on. That data, the raw data, has been provided with context. Okay. Now there's other things we know about the Social Security number. And by the way, I didn't even write Social Security number. I wrote SSN. And inside of everybody's head, I know you're thinking, oh, Social Security number. Okay. That too is knowledge. But what is a Social Security number? Okay. What other attributes are there associated with it? It's unique text. And by the way, text. Let me pause there. Not a number. Why is this Social Security number text and not a number? Can anybody think of why that might have, that's a requirement?
It's not one number, it's multiple numbers put together.
You could look at it that way, but
it starts with a 0.
You got it. Yes, starts with a 0. If this were a number, what would the computer do to that 0? Get rid of it, right? What number is 004? It's 4. So the computer will just, of course, perform that mathematical, truncation and get rid of leading zeros, where that leading 0 is relevant, okay? So we have to look at that. Going back to our abstraction and symbolic representation, we really have to think about how do we take this real world and put it, record it, represent it inside the computer. So that's kind of the first part of our studies into computer science. So we know it's text. We know what is a Social Security number corresponds one-to-one. There's a one-to-one relationship between a Social Security number and an individual. That too is knowledge. Okay, we haven't encoded that yet, but we should try to. We try to push data as far up the information hierarchy as possible. Going back to the Social Security example, why? Well, China, every country has some kind of identifier for its citizens. And if we can encode that, and who knows, China has one. If we can encode that this is a unique text, it is associated one-to-one with an individual. And if we encode all these things, these encodings can be compared. And then we have translation between the systems with automation, okay? So that's one of our purposes as well. So this is the information hierarchy, okay? Data, pushing it up, hopefully, to information, to knowledge, to wisdom. And we can look at the temporal aspect, what is known and what we need to do, from a predictive perspective. So if we look at, say, the stoplight example, what do we have? The raw data, the light is red, okay? Where is this light? Well, it's on some corner, right, at an intersection, okay? The context, further context, knowledge, I'm driving towards it. What do I need to do? I better stop the car. At a rudimentary level, I've actually just looked at, say, robotics programming, automation of cars, driverless cars. This is what we need to embed into the programming, okay? It's an analysis of the elements, the attributes, the state of the environment, and then make a decision in the future that'll hopefully be safe. Okay, so again, what you see here is I'm trying to shed light on some of the processes that we must take as computer scientists to encode, to represent the real world in computing. And we're going to look at this continually throughout this course. Okay, so again, as I stated at the beginning, any introductory study, is kind of a study in classification, categorization, a view from 20 or 30,000 feet. Many disciplines look at the evolution of the discipline because it lets us know, it grounds us. It's probably the best way to say it. So many of these disciplines look at, say, generations. In computing, we do the same thing. We look at generations of hardware. The textbook does not go into generations of operating systems, but there were generations of operating systems. And as each successive generation of hardware came about, there were kind of corresponding advances with the operating systems. The textbook does present programming from a generational perspective, and these two kind of went hand in hand, lockstep with the hardware generations. So, pre-computers, okay? So before any generation, there was computing was being done. You can look at the abacus, the slide rule, mechanical calculator, etc. One of the things that I've always found interesting, and it's always omitted, I've never seen it listed in any textbook, is, say, a weaving loom, pattern, textiles, things like that. They followed an algorithm, 2 strands of red, 1 strand of blue, several strands of white. This is an algorithm, okay? Programs, of course, are based on algorithms. So I'm really surprised that no author has ever included that as well. And in many cases, they used something similar to like punch cards to control that. So it's actually more closely aligned to computing than, say, an abacus or a slide rule, which are really for mathematical computations. Okay, first generation of language computers. The hardware involved were vacuum tubes. Okay, great. We have computers, and the time frame, by the way, 1946. Actually predated this a little because they were using the first computers in World War II to predict or analyze trajectories of missiles. So it's a little bit before 1946, but we'll leave it at that. There was no operating system. There was no programming language other than the machine language, the instruction set. So if you wanted to change the programming of the computer, you actually had to rewire the vacuum tubes. If you wanted to change the data set, you had to rewire the vacuum tubes. So first generation of hardware had no operating system, no programming language, zeros and ones, machine language. And again, we have a chapter on this, and I have a simulation. I will show that. So we'll look at this in far more detail. By the way, just anecdotally, it was actually Grace Hopper. She ended up being an admiral in the Navy, but she was one of the first programmers. And one of these early computers broke down. And actually, I think a beetle had crawled in and like separated one of the vacuum tubes. And the term debugging, when she fixed the computer, she said she had debugged it. So there you go. Second generation. Second generation saw the emergence and introduction of transistors. Far better than vacuum tubes. Vacuum tubes, of course, are hot. They take a lot of energy. They take enormous amounts of space. So transistors, in accord with Moore's law, we're cutting the size of the computer and increasing the processing capabilities of it. So much smaller, more powerful, use less energy, etc. We also saw the introduction of punch cards and magnetic tape for input and magnetic tape for storage. This is the beginning of the operating systems. Okay, You'll hear me say this over and over. We have a full chapter on operating systems. Operating systems are the resource managers of the computer. They manage peripherals. So in today's world, of course, mice, keyboards, monitors, things like this, but all resources. And we'll look at resources down the line, both physical and virtual. By the way, I use these terms interchangeably, virtual is the same as logical. Okay, so I will try to introduce all terms, equivalent terms. Maybe the textbook may not use them, but you'll find them in your other studies or other textbooks. So I'll try to introduce that as well. So logical equals virtual. Okay, so we have our first operating systems. We also started to see we had machine language, we saw the first programming languages. And I'm not going to talk about assembly language now, but that was the first programming language widely used. So I'll defer that. Moving to third generations, we saw the introduction of chips. We saw integrated circuits, which are tiny silicon chips. Okay. We saw the evolution of input and output. And again, we have a full chapter on input and output coming up. So we see the introduction of keyboards, far better than punch cards or magnetic tape, because there's visual input. And then monitors, of course, visual output as well. And we saw the introduction of magnetic hard drives. Okay. Fourth, I mentioned operating systems. We also saw the first multitasking operating systems during this time frame. But again, I'll talk about that when we get to operating systems, so I'll defer that at this juncture. Fourth generation, we saw microprocessors, chips, as we know today, okay? So we see things converging onto the chip, and that has continued. You know, you look at Apple's M1 chip, we see more and more things going onto a single chip. One, things are going to be closer together. So the transmission latencies between various components is going to be shorter. It's going to be faster. So we're seeing now the introduction, evolution to system on a chip. You know, the Wi-Fi network interface card, everything is going onto that single chip, which is great, you know, but does have some drawbacks too, okay, in terms of slowly improving your system, you know, upgrading different components of your system. If it's a single chip and you want to upgrade, you know, what you can do is, you know, throw out the chip or computer, probably computer, and buy another one. Okay, fifth generation. Fifth generation is entirely speculative. Nobody knows. Throwing darts here. It's been surmised it'll be based on artificial intelligence. One of the things the textbook doesn't include here is quantum computing. And we'll talk about that just a little bit in hardware. Optical computing, also known or alternatively known as photonic. Of course, photons are light. Okay. Tiny computers that utilize nanotechnology. Okay, are they connected? Is it a fully, you know, widely distributed system? Okay, is it a distributed operating system? And then, of course, embedded devices. Again, just from a classification perspective, where are we today? You know, it's characterized as pervasive or ubiquitous computing, which means computing all the time, everywhere. You know, we have our phones with us, right? I have a computer with me. If my phone doesn't have the processing power or the resources, I can, of course, I'm connected, hopefully, I have a connection, and I can avail myself to cloud computing resources. So both processing and actually data. Again, we're also seeing convergence. I mentioned yesterday, you know, the convergence, typically, you know, I use the cell phone and the camera, okay? And I do it, again, just to remind everyone that we need to continually assess that IT, business, society triangle, okay? Change to business is going to drive changes in IT, drive changes in society. Changes in society, you know, this lockdown, pandemic, whatever, you know, changes to business, Zoom, okay? Changes to IT, yes, we need to adapt to this new online environment. Going back to the cell phone and the camera, it's great. We can snap pictures everywhere, but problems arise. People will abuse it, take pictures where they shouldn't, children's playgrounds, locker rooms. And there's always going to be a lag, you know. The convergence happened, but legislation, laws coming out to prevent pictures in locker rooms lagged by about 2 years. There's always going to be this lag. It's our job to hopefully predict or foresee how any new technology can be abused. So, pardon me. Okay. Pardon me. So, when I look at when I look at a computer, I can distinguish between hardware and software. Software I can further distinguish between system software and application software. Same thing with hardware. I can distinguish between, hardware inside the computer or hardware outside the computer. When we look at external hardware, typically we can also call it peripherals, okay? Your keyboard is a peripheral, your monitor, your printer, things of this nature. So input devices and output, I'm not going to say much. Again, we have an entire chapter on it, so I'll just let you read. I'm not going to regurgitate, include keyboards, mice, scanners. So the textbook is missing several things, though. One, sensors for the Internet of Things, and the Internet of Things is here, whether we recognize it or not. Maybe it's better whether we acknowledge it or not. And this is going to have a lot of ramifications, especially in society. It's already shown that in business. Give an example. Best Buy. Best Buy put cameras at the front of their stores. This is, the late 2000s. And they looked at it, they looked at the data, and they saw that 75% of the people, when they walked into a store, they looked right. Think about when you walk into a Best Buy right now. Where are all the expensive items? So you're seeing from a business perspective, the result of that new, introduce a term here, dark data. Dark data is data that was previously unknown. So it was discovered, Internet of Things, through sensors. A lot of issues here. Security, tracking, location, privacy, things of this nature. And we'll investigate that thoroughly. Processing devices, central processing unit, graphical processing unit. And again, increasingly, we're seeing this on a single chip. Output devices, monitors, printers, speakers, things like that. What the textbook doesn't include, haptics. Okay, haptics is sensory. See this in our cars, right? You're driving in a highway, you cross a lane, get close to the yellow lines, and your steering wheel vibrates. Sensory feedback. Because quite often that catches our attention quicker than, say, in audio. By the time someone says, "Up, lane detection," I would have felt that and reacted to my steering wheel vibrating, which I hate, by the way. Have it turned off. Our seats in cars, newer cars, you're backing up for collision avoidance. And if your car detects you're about to hit something, your seat will vibrate, which allows me to quickly step on the brake. Okay, so haptics. Haptics have a lot of applications also in simulation. Okay, I'll let you know. I'm ex-Navy. I was a Sea Air Rescue Hospital corpsman, and of course, we'd have to practice on each other for inserting IVs, things of this nature. How do we do that in this online world? I look at nursing students, nursing programs today. How are they going to accommodate this? Haptics, you can actually get that sensory feedback of actually putting in an IV. Storage and communications devices. Again, we have entire chapters on storage and actually several on communications devices. So I'm not really going to talk about those now. I'll let you read it. We know storage devices used to store data. Okay. And I'll leave it at that. Software. Software, again, there's a distinction between system software and application software. By the way, I have allergies too. So when I look at system software, the most conspicuous piece of system software is that operating system. And I'll say this now, and I'll repeat it several times, and I'll look at it in further and further detail. The operating system is the resource manager. It's the policeman. It governs all activity on the computer, okay? If you want to print a file, you're not printing a file, your computer isn't, it's the operating system. Microsoft Word is not printing the file. Microsoft Word is asking the operating system to print the file. So, and I'll get into this in much more detail in the chapter on operating systems. Security begins, doesn't end, but begins with the operating system. Now, when I look at the operating system, it's the resource manager. It is responsible for getting the computer up and running. Of course, these are instructions. Please research the boot process. And it has recently, newer computers, we've moved to the Unified Extensible Firmware Interface from the legacy BIOS. But functionally, the same things occur, okay? UEFI has many advantages over the former legacy BIOS, and I won't get into those now. I'll get into them when I cover operating systems. What occurs, though, to boot a computer? You turn the power on. The first thing that happens is the power on self-test post. Power on self-test. So it checks, the instructions. Do you have a keyboard? Do you have a monitor? Do you have memory? If so, how much? Do you have a hard drive? Are you connected to any printers? Things of this nature. What resources are available? Remember, the operating system is the resource manager. It then loads the basic input-output system. Remember the basic functionality of a computer: input, processing, output. You can't do any processing if you don't have input and output. So the first thing a computer needs to get up and running is the ability to take input and the ability to put out output. Okay, so we have the post, power and self-test. Next, it loads the BIOS, basic input output system, and then it jumps to the master boot record in storage and loads the rest of the operating system, or the kernel, for those of you who have already written Linux, the required Linux material for this week. These instructions, okay, these first instructions to boot up, are located in either non-volatile RAM or electronically erasable, programmable, read-only memory. And again, this is coming. We'll cover this again in operating systems. You're not required to know it now, but I figured I'd introduce it. Okay. Application software, probably the easiest chapter in the text. Why? Everybody uses it, right? You use email clients, you use apps on your phone, Microsoft Office, etc. I won't go into it at this juncture. Same thing, I'm not really going to cover at this point in time, computer users and professionals. The way this, again, from a generic, general presentation, this first chapter, what does a programmer do? Writes programs. What does a systems analyst do? Performs systems analysis. So at this level, with our understanding, we just haven't covered enough for me to get into, what each one of these individuals really does, but it's fairly straightforward. I can ask the question, what do you think a database administrator does? Administers a database management system. So I won't cover this at this juncture. Again, this chapter, we're just kind of describing, categorizing. So there are categories of computers, okay? Embedded computers are everywhere these days, whether it's cars, sewing machines, refrigerators. But I want you to keep one thing in mind, and the textbook doesn't actually present this. As soon as I put a computer inside a device, that device inherits all the vulnerabilities of computers. So I'm talking about security. As soon as you put a computer in a device, it can be hacked, okay? Especially if it has a network connection. And for most of the embedded computing that's being done today, they all have, whether it's Wi-Fi, Bluetooth, something, they have some type of networking functionality. So they're hackable. So think about this, and I'm going to introduce some frightening things about what's been done to cars, but also medical devices. Pacemakers can be hacked. And I'll stop there until we get to our chapters on security. Mobile devices, again, I'm not going to say anything about this at this juncture. It's very rare that someone doesn't have a mobile phone. In all honesty, I wish I didn't have one, though. I'd rather not be connected 24/7. I'll leave it at that. Portable computers, notebooks, laptops, even an iPad. Whether an iPad's a mobile device or a tablet, computer, and so these definitions aren't hard and fast, okay? Quite often things bridge the classification system. Okay, thin clients. Well, before I talk about thin clients, I'm actually going to skip a slide and talk about servers. Client server computing. Okay. The classic example is to use, say, a restaurant, even Burger King, McDonald's, anything. You walk in, you're the client, you request a resource, in this case it's food, Big Mac, whatever, and they serve it to you. In the case of computing, a server will provide you with a resource. An email server will forward your emails to you. An application server will allow you to run, say, Microsoft Office from the cloud. Okay, storage servers, Box.net, Dropbox, iCloud. So they host, storage for you. Okay, now back in that third generation hardware computers, we essentially had mainframe computers, and you had, dumb terminals. Okay, so keyboard and monitor, and all the computation would take place on the mainframe server, and of course the output would be sent to the monitor, and input would be taken from your keyboard. If you watch old movies, you can actually see all these data centers, with lots of people working in them. Well, that was great back then. It was text only, largely. Today, of course, we now have graphical user interfaces. We have all this multimedia. Well, with all this multimedia, the bandwidth requirements shoot through the roof. So it's actually better in some cases to do some processing locally. So rather than a strict client-server environment, provide a thin client. A thin client will get most of its data and some processing from the server, but it can also do, say, graphical refreshing here locally. So I don't have these screens, which consumes a lot of bandwidth, continually passing between the server and the client. The server is no longer responsible for refreshing my screen. By the way, hopefully I'm using my hands. Hopefully that's not distracting anyone here. Moving to the online environment, trying to teach through Zoom is different. Virtualization. We are going to look at virtualization in depth. It is here, it's the present, it's the future. In Linux Lab 9, everyone will implement their own virtual machines and actually install an Ubuntu operating system, Linux, into that virtual machine. I'm not going to say any more about it now, but virtualization is used highly in the data centers as well. There are many benefits, both on the desktop and in the data center. If you buy a server, it's almost impossible to use that server effectively, okay? It's largely going to sit there unused in terms of computing cycles. It's going to be latent for a large part of its time. Whereas I can purchase a single hardware server and I can virtualize it. I can put 3 different operating systems on it. One operating system will run an email server, one an application server, one a web server, etc. Storage server, 4th one. So I can use the CPU effectively and always keep that CPU running. Far more cost effective than me buying 4 servers, one for each of a web server, email server, etc. Mainframe computers. Well, by inherently, a mainframe computer is a server, okay, used by large organizations to store data. So you have clients accessing it for many different reasons. So again, the distinction between servers and mainframe computers, well, a mainframe is a server. Largely, probably, I don't have any data on this, so I'll just guess, 50% of the servers out there may themselves qualify as mainframe computers. Who knows? Supercomputers. Supercomputers are distinct, okay? Primarily because they generally run one program at a time. So we look at, say, weather forecasting, things of this nature, space exploration. And they're few and far between. And if they're not continually updated, they don't remain they don't remain there or keep their classification as a supercomputer for long. So, we're looking at, the NSA, the computers at Palo Alto, things like that. Computer networks, again, we have an entire chapter on this. And actually, if you look at computing today, we rely on networking. I can't imagine any computers coming out today that don't have networking functionality. Okay, we take it for granted. Um, it would have limited, you know, efficiency of effectiveness if it wasn't networked. At this juncture, with the internet and World Wide Web, just know that the two are not the same. The internet is the network, it's the infrastructure. The World Wide Web is linked information. Now, the World Wide Web is the publicly visible information. In this course, we're also going to explore the dark web, okay, or the deep web. It's been said the deep web has 500 times more information available than what's on the World Wide Web, the visible web as we know it. And it's used for both good and bad. The dark web, yes, it's being used by terrorists, organized crime, drug dealers, and the like. But there's also viable information out there on it. So again, I'll defer my presentation on that until later, until we actually get into the internet. So to access the internet, you do need the necessary networking hardware, which is the network adapter. And again, we're going to look at this in the chapter on networking. So I'm not going to look at that in more detail at this point. Internet addresses. Okay. An IP address, okay, as an example here, is a virtual or logical address. Much the same way that your cell phone, your telephone number is, right? You can buy a new phone, trade your phone in, and bring your phone number with you, which means it's not hardwired into the phone. It's associated with the physical network adapter, the SIM card. Again, I won't go into the functionality of that, but IP addresses are logical or virtual. Remember, the two are the same: logical, virtual. Okay, we've recently seen the evolution from IPv4. Okay, where IP addresses are 32 bits or 4 bytes, and I can see this represented here. Okay, the bytes are separated by the period or dot, to IPv6, which is 128 bits, largely because addressing space. Okay, and I'm not going to get into addressing space now. I'm going to cover this when I get to hardware, but I want to introduce it so that when I do cover it, it strikes a chord. Domain names. Okay, so top level domain names, .edu, hvc.edu, .com, .gov, things of this nature. Uniform resource locators, URLs. Very important for us humans, okay? I use this example too much, so I might as well introduce it now. I follow sports. If, fortunately, there's a URL, espn.com, right? I can walk up to a kiosk in Florida, in the browser, espn.com, and get there. If I had to remember ESPN was 64.82. whatever, and that would be okay, with 4 bytes, IPv4, with 128 bits, there's no way I'm going to remember 16 bytes, that address. So I'm not going to say much more about that. I'm going to say nothing about email addresses, except that it's, a username separated by the @ symbol with the domain name. I'll leave it at that. There's all kinds of etiquette that goes along, online communications. And we're thrust into this online world. But actually, we preceded this, with what's going on in the world as computer scientists, because we have been outsourcing, consulting with groups that we never meet physically. Again, our written word is our first impression quite often. Cloud computing. There is no great mystery to cloud computing. What is cloud computing? Client server computing, right? Cloud computing, it's up there in a server somewhere. But what's made it ubiquitous, okay, or easy to use, is now we have a web interface. In the past, it would all be proprietary. With a client server, you'd actually have to program that interface. And it wouldn't apply to all client server environments. Now, the cloud server, all it needs to do is format its output into, say, a web page, HTML page, and it can be rendered or represented on every device on any computer, any mobile phone. So cloud computing, no mystery whatsoever. All it is, client server computing with a web interface. And as soon as you provide that web interface, pushing out the web, the HTML, any device can look at it, okay? So you've just made it highly usable, highly accessible. Surfing the web, I think everybody's probably pretty familiar. Searching the web, we are going to look at this in depth because this has changed, and it's changed without people's awareness. I first became aware of this, back 2010 or so, when I saw that, Google was actually leading people to what it thought they wanted to see or what it wanted them to see. Okay, and there's a lot of things going on, with information misdirection, censoring, and I won't get into that, from a political standpoint. But from an academic research perspective, if I'm doing research, I need to see everything that's available. I can't base my research just on what Google wants me to see. There's this whole other area, valid facts, that Google is not showing me anymore. I use DuckDuckGo as my search engine. I still use Google. I still contrast them from a research perspective because it lets me, it kind of reveals what Google wants me to see and doesn't want me to see. So this is very real taking place. So from an academic research perspective, I don't see it as a positive. Email. Again, I'm not going to say much about it. So technology and society. And again, I present this a little different than the text. I introduced that IT business society triangle. And whenever there's a change to any one of those vertices, whether it's IT, a change in business, a change in society, it's going to drive changes in the others. It's very difficult to foresee all possibilities. In CISS100.com, I gave that example. Native, South Americans, some, tribe, happen upon a car, sitting there in the middle of the rainforest, and they can see its utility. They can get inside it. They can look through the glass. Maybe the lights still work. Inside the car, they're probably protected from predators, things like this. So they can see the utility, but they don't see its use, its application in the bigger picture, as in driving down a highway. And quite often that's what occurs to us with technology. Some new technology comes out and we go, oh yeah, highly useful, but we don't see it in the bigger picture. And it's very hard to do. But hopefully over time, we get better and better at it, assessing all the possibilities, all the risks. So there are a lot of risks with technology, and we'll look at these, in turn. One, we're living in this electromagnetic, radio frequency soup. And it's gotten worse. We're going to learn in networking that bandwidth depends on the frequency. Okay. And you can kind of see this, draw with my finger here. If I have a very long wavelength, and this isn't the way it's done, but I could record a 1 and a 0. Where in that same time frame, if I had a high frequency, I could record a lot of zeros and ones. And that's what's being done as we move from 3G to 4G to 5G. The frequency is getting higher and higher. What is it getting close to? This is all the the microwave electromagnetic spectrum. We're getting closer and closer to the frequencies that we use in our microwave ovens, right? Is this good for our bodies? So there are a lot of issues here with technology: privacy, location tracking, artificial intelligence, profiling, predictive analytics. With facial recognition, they can now look and say, good mood, bad mood. Google has patents that will change the way it interacts with you based on your mood. So these robots that Google is developing will look at you, say, oh, he's in a bad mood. I need to change my behavior this way. Is that good interaction or is it manipulation? I don't know. I don't have an answer. It's just asking questions at this juncture. Okay. Technology online, we know about netiquette. We know about anonymity. People will say things online they would never say face to face. There's studies out there. MIT did a study on Facebook and found that Facebook users feel worse about themselves than non-Facebook users. Okay. Oxford University in England did a study contrasting email with regular mail. They'd send the same message via email rather than in like a post letter, and people would take exception to it and object to it when they received it in email. But if they got the same letter via mail, they're like fine with it. There's something different about electronic communications. It's just more personal. So that's it. That's the end of the chapter. So again, by Sunday night is discussion board 1, just your introduction. Make sure you read Linux Lab 1. It's just reading. Make sure you read it. Read the textbook chapter 1 and perform that quiz. And there's also that introduction and syllabus quiz. The introduction syllabus quiz, you have all the time you need, and you can take it over and over, get a good score, pad your score. The chapter quiz is timed and you get 1 attempt. So do not close your browser, do not hit back. And again, I know things come up. If something comes up and you can't make a deadline, just let me know in advance. And I understand, you can't let me know in advance of everything. God forbid a car accident, something like that. But just keep me in the loop. That's it. I'm highly available. And that's it. If you have any questions, I'll be around here, and have a great week. See you next Tuesday.
Thank you. Bye.
Thank you. See you.
James, for that Linux lab, all we have to do is just read it through fully.